friend. Study with Apala. Chapter 3, Geological Work of Natural Agencies. Thermal effect in solutions. In arid desert and semi-arid regions where summers and winter temperatures different considerably, the rocks undergo physical disintegration by another phenomenon related to temperature. As we know, rock, like many other solids, expand on heating and contract on cooling. So they rock are of course classed as bad conductors of heat events, but even then prolonged exposures to the direct heating by the sun does includes appreciable volumeter sorry volumetric change in them. So in arid and semi-arid region, the difference between day and night temperatures and also between average temperature in summer and winter is quite considerable. In some deserts, for instance, Karakum rocks are exposed to as a high temperature as 70 to 80 degrees Celsius in summers, and are then cooled down to minus 10 degrees Celsius in winter. Such repeated variations in temperature experienced by a body of rock gradually break it into smaller pieces, especially in the top layers, by development of tensile stresses developing from alternators, expansion and contractions, exfoliations in a thick rocks bodies or where the rocks is layered. These are the upper layer that get affected most due to the temperatures variations. As a result, the upper layer may virtually peel off from the underlying rocks mass. In many cases, such a change is also accompanied by chemical weathering, especially at margins and boundaries of the separated layers, developing a curved surface. This phenomenon of peelings of curved cells from the rock under the influence of them thermal effect, as resembling in some details with the spheroidal weatherings that result from predominantly the chemical weathering on smaller rocks blocks and is described separately. Unloading. This is another process of mechanical weathering, where large scale development of fracturing in confined rocks masses is attributed to removals of the overlying rocks cover due to the prolonged erosional work of other agencies. These rock masses remains confined from sides, but due to relief of pressures from above, so they expand upward. Consequently, joint develop in them parallel to the upper uncovered surface, dividing them into sheets. This rupturings or jointings is in itself is a mechanical breakdowns of rocks and makes them available for further weatherings or decays along the joint planes. It is believed by many that unloadings of deeply buried plutons is often the cause of development of concentric joint in them. Further, mechanical weathering along these joints lead to peel of slabs and converting the plutons into an exfoliation domes. Chemical weathering, it is a process of alterations of rocks of the crust by chemical decompositions brought about by atmospheric gases and moisture. So the chemical change in the nature of the rocks take place in the presence of moisture containing many active gases from the atmosphere, such as carbon dioxide, nitrogen, hydrogen, and oxygen. As we know, rocks are made up of minerals, all of which are not in chemical equilibrium with the atmosphere around them. So chemical weathering is essentially a process of chemical reactions between the surface of the rock and the atmospheric gases in the direction of establishing a chemical equilibrium. The end product of chemical weathering has a different chemical composition and poorer physical constitution as compared to the parent rock. Chemical weathering eats up the rocks in a number of ways depending upon their mineralogical composition and the nature of chemical environment surrounding them. The following are some of the main process of chemical weathering: solution hydrations and hydrolysis, oxidations and reductions, carbonations, base exchange and formation of colloids. Solutions: some rocks contains one or more minerals that are so, uh, sol- solubles in water to some extent. Rock salts, gypsums, and calcite are few common examples. It is also well known that though pure water is not as a good solvent of minerals in most cases, but when the water is carbonated, its solvent actions for many common minerals is enhanced. Thus, the limestone is not easily soluble in pure water, but carbonated water dissolves the rocks effectively. Limestone get pitted and porous due to chemical weathering, hydrations, and hydrolysis. These two processes indicate the direct attack of atmospheric moisture on the individual minerals of rocks that ultimately affect its structural makeup. It is believed that though the interior of many minerals is in electric equilibrium, so the surface of many crystals are not. They may have partially unsatisfied valencies. Once a polarized water molecules comes in contact with such a crystal, it may cause any one of the following two reactions. First, the ions tend to hold the polarized size of the water molecules and from the hydrate thin this process of addition of the water molecules is termed as hydrations. Examples are provided by hydrations of iron oxide and calcium sulfate crystals in some minerals with the ferrous irons. The Fe plus 2 charge ions hold the water molecules and form water iron complex or hydroxide. Similar to calcium sulfate CaSO4 also anhydrides get slowly converted to gypsums by hydration. Don't forget to write formula. Practice many times. So CaSO4 anhydride calcium sulfate plus 2H2 water molecules and vector CSO4 2H2O make gypsum. So second, ions may be exchanged whereby some ions from the waters may enters into the crystals lattice of the minerals. This process of exchange of ions is called hydrolysis. It is very common process of weathering of silicate minerals which are quite abundant in rock and is best explained with the reference to weathering of minerals, orthoclase, and as a feldspar. So learn orthoclase and feldspar formula. There are many use in this field, in this subject. K potassium's orthoclase plus AlSi3O4 iron of water and plus this hydrogen plus charge HAlSi3O4 make silicic acid like structure plus Cape iron pot iron. So oxidation and reductions. Iron is a chief constitutions of many minerals. Oxidation and reductions. Iron is chiefly constituted of many minerals and rocks. The irons bearings minerals and hence rock are especially so prone to chemical weatherings through the process of oxidation and reductions. Oxidations ferrous irons Fe plus 2 charge of minerals in is oxidized to ferric iron plus 3 charge on exposure to air rich in smush. So ferric iron is not stable and is further oxidized to a stable ferric hydroxide. This formula 4Fe plus 3O2 iron oxygens make a 2Fe2O3 pyrite. Sorry, make a ferric oxide Fe2O3. Fe2O3 plus H2O, Fe2O3 to H2O. Similarly, pyrite FeS2, naturals and common iron minerals are present in many rock in small amounts. Examples in limestone and may undergo oxidation and hydrations in a sequence forming sulfuric acid in the process that may further corrode the carbonate like carbonate rock limestone. 2 FeS2 means pyrite plus oxygen, 7 molecules, 7O2 plus 2 H2O water, FeS4 iron sulfide plus 2 H2SO4 sulfuric acid. Reductions in a specific type of environment such as where soil is rich in decaying vegetation, swamp, minerals and rocks containing iron oxide may undergo a reduction of the oxides to elemental irons. In this case, the decaying vegetation supplies the carbonaceous content, causing reductions. The effect of oxidation and to some extent of reductions weatherings are easily observed from the colors change produced in iron bearing rock, those rocks in which the iron has been oxidized to ferric state, so a marked brown color, especially in oxide, hydroxide and hydrates, but where the oxidation has reached only the ferrous state, the typical color developed in the rock are various shade of green, blue and gray. Thank you.